Yeah, I don't know how many of you paid attention to this, but Apple just made an announcement of a new product lines, right? And one of the major new revision, new model is this Apple Watch, and they released the models 6, and they improve the health monitoring capability, and it's very timely because we just released the context-oriented project 1, and that's focuses on the wearable health monitoring systems. And let me just share some of the interesting. We just what we are waiting for other people to join. So this is the new iWatch, and inside of it, basically having a 4 lights instead of a 2, which is mine. And this guy is to measure saturated oxygen level. Yeah, and what's the film? Maybe blood, stuff. So SAT-O2 saturated oxygen level is very important. And then at this time of pandemic, that the once you got the coronavirus, and then young people like you are okay. However, in an unexpected event, the situation gets worse. It happened rather quickly, right? And that's basically that the virus attacked the pulmonary systems. So they SAT-O2 saturated oxygen, indicating how much oxygen is being, transported through the circulatory system. That one plunges. Usually 95 or 96. That's actually healthy people, but a plunge to less than 85 or something. That's really a big warning situation. So wearable systems can detect that all the time. So that's really, Apple doesn't say that explicitly, but they just focus on the fitness and some simple use. But in fact, that's actually a renewed interest. And then the key technology there is how you assure the good signals despite the motion, because of wearable, the motion, right? So we put the accelerometers, IMU in it, and to recover the signals. So that's one of the topic we discussed today. So it sounds pretty, timely. Okay, so and then we also released the chapter 3 and the lecture notes. So please look at that. In addition to the the videos. Okay, so with that, let's start today's class. So let me see. It's going to full screen, and yeah, here we go. So this is lecture 4, random variables, random processes. So you know what? So far we look at the estimation of parameters in the deterministic systems. But I know this deterministic system is a little misleading, because we dealt with the signals like this, and obviously they are corrupted with noise, right? But the recursive least square, we basically examine only the difference between predicted and actual signals. And actually, we try to minimize the squared sum of all these sample points, right? That's a very natural, simple way of handling this to find the best fit, in terms of these parameters. However, we haven't exploited, we haven't quantified the property of the noise. right? Instead, if you really knows the properties of the noise and quantify them properly, we can utilize that knowledge to better estimate this, right? So dynamical system we deal with, and if noiseless, it's a very straightforward problem. But in fact, noise comes in through say the plant is disturbed, and a car, running on the rough terrain, actually, having some kind of a process noise. And if you take a measurement, that comes with some noise, right? So knowing the properties of these noise and then understanding how the noise comes into the systems, the structure of the noise, process, it will be useful for better estimating the plant or the parameters involved. And also having that kind of understanding is allow us to better understand the properties of the estimations. Okay, with that, we like to introduce the probability theory and the random variables and the random process. And this part is something we need a quick review. For course 2 students, I know if you have undergraduate studies in course 2, mechanical engineering, having less opportunities to study or review probability theory, course 6 and course 16 students, you deal with the probability all the times, so no need to review it, but just to unify the background of the students, and I like to make some quick review. I want to go too deep, but I know more rigorous treatments have been and provided in the set theory or sigma field and Lebesgue measures. Some of you have no idea about this, but that's okay. That we will not go too deep into this. Rather, just things that we need to use all the time. Most of them you did it in somewhere in the high school, but it's time to review it. So for those people who knows this very well, just take a rest, relax, and I'll send you the wake-up call when it's going to something important. Okay, so the first item is random variables. And it said the random variables is a function. This is very confusing. Why the variable is a function? But in fact, it is a function whose name is random variable. It's a function because it maps a random event, such as throwing the pair of the dice, map that one to a numerical value, such as the phase is 6 and 6, and so in total 12. That's mapped to a numerical value, right? Now, it has actually a probability distribution on 6, 6, or 1, 1, the hardest to obtain. But I know total of 7, maybe more actually likely to occur. So we have this kind of probability mass function for this discrete event systems. Now, in notation, we use a capital X, capital, for describing the random variable, and a particular value or instantiation, we use a lowercase. And in probability theory, this distinction is very important, but I know in engineering, we sometimes abuse the, we don't follow this rule. But basically, a capital X is a random variables, and the lowercase is a specific value instantiation. Okay, cumulative the distribution function. This one is the probability that random variables takes the value X or lower, and so this capital Fx is take the value between 0 and 1. It is non-decreasing function like this. It's called CDF. Now, yeah, we perhaps you are familiar with the probability density function more. And probability density can be derived from cumulative distribution function. And I know you just take the derivative with respect to this. That is actually definitions of a density function. And in fact, as you integrate this, you get the original cumulative distribution function. And then if you integrate out, minus infinity to plus infinity, the result is 1, right? So something like this. This is the slope. That's actually a PDF. You know that the probability X is in a continuous, systems. If X equal, X probability is basically 0, right? On the discrete ones, it's not actually, but on continuous, event systems, X equal lowercase x is 0. In fact, to get the sum probability, you have to take this, cumulative distribution, or you have to set some kind of windows, the delta x, and multiply to this. So now the joint probability, you think about let's say two random variables x and y, and if x and y takes a particular values xi and yj at the same time, and then it's actually the probability of that is joint probability. This is a case for discrete, and a continuous case, because of that actually issue, you have to set the delta x and delta y windows, and within that area, you get the this relationship. Independent random variables is the case that the two random variables, their joint probability is basically the product of individual the densities and fx and fy. Conditional probability density is x slash y, conditional probability of x given the y, that the event y has happened, then what is the probability of x? This is given by joint probability fxy xy divided by fyy. So under the probability y, this is to give the conditional probability. Now, if capital X and Y are independent random variables, then this joint probability is replaced by the product of individual probabilities, and then Fy cancel out. So leaving that Fx, meaning that this joint probability does not depend on the other side of probability Fy. So that's actually depends on only its own density function fx. Bayes rule is one of the most often used, frequently used rules. So from conditional probability, f y slash x can be written in this way, right? Joint probability divided by the probability of x. So we can get the two expression for the joint probability, depending on which one to go downstairs. You get the two expressions, and looking at these two equations, we can write the one conditional probability as a function of the other. As shown here, fxy equal fyx, fx over fy. And this Bayes rule, we see it quite often. We use it in a Bayes filter and some reasoning. We see it quite often. Now, marginal probability, perhaps you remember that if you have a joint probability fxy, which is actually two-dimensional surface in this domain, and you pick a particular value of y, and then you integrate this along this x directions, and that is actually projected onto this plane. That's actually fyy, and that is represented here. The joint probability integrate out, with respect to one variable, and if y, fix the other x, that's actually marginal probability of fx, and this is the vice versa. We change the. I'm sorry, this one should be x, and oh yeah, this is correct. This y, that's correct. Yeah, this is correct. This one is this, and shown here is this guy. Yeah, this is correct. Yeah. Okay. Now expectations, so expected the value of random variable x is x times its density, and then integrate out, right? Well, this discrete case, we can put this one this way. Now, we can take expectation over any functional of random variable x. For instance, if x is basically x raised to the power of x k, and then that's actually kth moment, right? So x kth times the its the density, and then integrate out. A particular interest is actually k equal 2, and then we multiply this density. However, we take this x from its own mean value, and then that's actually in the variance. So subtract the mean, and then we take the expectations of the square of them. And then this inside of this expectation can be expanded this way: x squared minus 2x ex squared. But now this can be distributed because expectation is nothing but the integral operation, and that expectation can be taken individually. So first one ex squared. The second one, if you look at this ex, once you have taken expectation, this particular value ex, which represents the mean, is no longer a random variable. It's just a constant. So we can factor out, So expectation applies to only x, which is actually this guy, right? And then this way the constant. So, coming out this way, and then these two, partially cancel out, and leaving, this expression, variance x equal expectation of x squared minus mean values square. This is something we often see. Okay, with that, the mean and variance, we can actually define the normal or Gaussian distribution, as you have seen this exponential expression. You remember this, So this is the scalar case. We can expand it to multi-variables case in a simple way. So now we are getting into a little bit more important and actually tricky part. So first thing is a correlation. So correlation is the expectation of the product of two random variables, x, y. Okay, so set the product here, and then multiplied by the joint probability density, and then integrate, for both x and y. That's correlation. Okay, this is the definition of correlation. Now, a special case is x and y are independent. Remember, independent is the case where joint probability is given by the product of individual densities. So fx times fy. So this integration can be split into these two, and each represent a mean. So if the two variables are independent, correlation is the product of mean. Okay. Now, one very important concept which we often see is orthogonality. Orthogonality is defined in this way: if two random variables x, y, and if you take the correlation, if correlation is 0, then x and y are said to be orthogonal. Okay. Now, I know, sometimes the people get confused orthogonality and independence. So, even though, expectation xy equals 0, correlation is 0, xy is not necessarily independent. These two are totally different concept. As a matter of fact, if they are independent, it is given by this. So if one of these two variables, x or y, is basically, mean 0, and the mean value is 0, it makes this correlation 0. So it's basically also orthogonal. But when you look at this, correlation turns out to be 0, does not really mean that the two variables x, y are independent. This orthogonal condition is met even though x, y are not actually independent. So please be careful about that point. Okay, now covariance is actually just just a minor modification to correlations. Instead of taking the product between x, y directly, but we instead subtract their means ex and ey, and then take the product and take the expectation. Now, correlation coefficient, or more specifically Peirce, correlation coefficient, is somewhat more normalized version of this correlations and covariance. And it is to normalize covariance by each random variable's variance, square of variance x, and then square of variance y. Well, it can be actually written in this way. So first, the random variables, we subtract the mean value and then divide it by standard deviations, by basically a square of, variance is basically standard deviation, sigma x and sigma y. And this normalized expression is to represent how x and y are close to the linear relationship. So if say variable y is actually purely linearly related to x, y equal a times x, for instance, these two are totally correlated, and basically this one is take the value of 1, and so let me see. Okay, so here, let's see, this one is x, and then this one is, y, and if all the points are on the straight line, positive, line, then it is actually, it takes the value of 1. Instead, points are all distributed, and, even at this point and at this point, so, all distributed, it's basically no correlation. Actually, it becomes 0. Yeah. So by evaluating this, so we can see, how much, linearly, correlated, and correlation can be found between the two variables. Okay. So up to this point, it's very, very, standard things, but we move into a little, complicated and an important the concept that's a random process. So just if you are not so much sure about the probability the theory, please review on your own. I think you have pretty good textbooks, and also I listed some recommended textbooks, just undergraduate the textbooks, and the lecture notes, which are lecture note chapter 3 at the end. I listed some recommended textbooks, so please review them. Okay, now our interest in 2160 is to deal with the more kind of time sequence data, time sequence data as opposed to just a one, random variables. This to introduce the random process. This is my preferred example. So this is oscilloscope, right? So when you use oscilloscope, first you don't put any signals into the input, but if you increase the gain, amplitude gain, higher and higher, so that the say one grid, corresponds to let's say 1 microvolt or 1 millivolt. You see this kind of very random noise signals coming out, right? So if you freeze it in this scope, you get this type of waveform. If you freeze it in different time, you get the different waveforms, right? So perhaps these two waveforms are coming from the same random process, I would say, right? But these two are specific values or instantiations of the original random process. If you have thousands of the same models or oscilloscopes, and then you freeze the screen at the same time, you get the thousands of waveforms, right? So if you collect all these waveforms, you can actually create a kind of ensemble or family of waveforms, and you can characterize these statistical properties among them. So let's say if you pick one time, say t, and freeze all thousands of oscilloscopes and read out the data, you can actually create a kind of histogram, or actually going to some distribution of the signals at the time t equal t, right? So this kind of process can be characterized as a so for each time slice, it turns out to be a random variable. It is a random variables. For each time instance, it is actually shows a random variables. But we are interested in the time sequence, so we collectively deal with many random variables along this line. So with such actually collections of random variables is called a random process. Okay, so we collectively called these random variables a random process. Does that make sense? Okay. So now let's characterize such a random process. And the first thing is, just as we discussed, it's a first order density, just to pick one time slice and characterize its distributions in a PDF. That's actually one properties characterization of this random process. But a more interesting part is that, since this is a time sequence, right? Time sequence. So you may be interested in examining how these values are related to just a one-time step back. Oops. Yeah. So not only just looking at this individual time slice, but what happens a few milliseconds before that. How this value and then the previous this value are related or correlated to each other. If you see some kind of correlation, that's one characterization of this process, right? So yeah, that's actually going to autocorrelation. Okay. It's a quantification of a random process by using the notions of correlation. Okay, so let's start with the two time slices, T1 and T2. Let us quantify how two random variables at two different times of a random process are correlated to each other. Okay, so x, t1 and x, the t2, be two random variables at the time t1 and t2. Remember, I know random process is nothing but collections of random variables. So if you pick the two time slices, you get the two random variables. Okay, that is denoted by this, and we can define the joint probability of x1 and x2. With this, we can actually write out correlation between the two random variables, right? That is actually expectation xt1 and xt2 products. We write it in this way: R sub xx, and then the t1 and t2. Okay, so by definition, it is written in this way: product x1 x2, okay, times joint probability fx1 x2, and then integrate out the dx1 and dx2. We have to integrate for both variables. Okay, this is called autocorrelation. Autocorrelation, because it comes from the same random process. It is to compare, correlate with its own actually past or future, values, random variables. Okay, now one important kind of assumption or premise that we introduce in the following analysis is called the wide sense stationary process. Wide sense stationary process. We need some kind of stationarity to do some meaningful analysis. Okay, so a random process is called a wide sense stationary process if the following two conditions are met. So stationary, so if you take the mean of this random variables, actually each random variables are here and here, right? At each time slice, it has its own density and actually distribution like this. For that distribution, let's first compute the mean. And wide sense stationary process, the mean is the same throughout this timeline. Okay, mean is actually the same and constant for all time t. That's the first property. And the second property is on autocorrelation. Okay, so autocorrelation, you pick two time slices, T1 and T2, right? And we computed the correlation between the two. But now in a stationary process, we're actually addressing, we assume that the correlation remains the same as far as actually the distance between T1, T2, let's say the tau, remains the same. No matter where you pick up T1, T2 along this line, as far as the distance in between is tau, you get exactly the same correlation, regardless of two time slices you take along this line. As far as the difference between the two is the same, you get the same results. So that's stated here. Autocorrelation depends only on the time interval, tau equal T2 minus T1, rather than the specific times T1, T2. So, we collapse these T1, T2 to just, one interval, parameter tau. So by definition, it can be written this way. It's expectation, xt plus tau, and then xt for all the t, okay? From this definition, so you can easily, find that, even though t plus tau is actually moved to this end, it remains the same. And then, even though you change this, row T1, T2 is swapped, it turns out, the tau becomes minus tau, but the actual result remains the same. So in a sense, as a function, this one is actually even function as shown here. Okay, now just separately from this story, autocovariance is basically a natural, variations to the original, autocorrelation. Basically, we subtract the mean value from 2 time slice random variables, and then actually, apply this covariance, notation to do this. Okay, so we just introduced the wide sense stationary process, and this is to allow us to define this autocorrelation in this way, which is just depends on the time difference between the two. Usually, if these 2 time slices are very close, we're looking at this T2, but the T1 is just a 1 time slice, back. They are usually more correlated, right? More correlated. And as the distance getting farther, it is to less correlate, less correlated. So, just finding this, autocorrelation as a functions of time interval tau, you can get some, useful insight into how this random process is behaving. And in fact, this autocorrelation is actually strongly related to power spectrum, which we learn later. And using power spectrum, we can do some effective system identifications and so forth. So that's very important, part. Another, the kind of a big premise, we often see in the, many analyses, is this IID. IID is the abbreviations of independent and identically distributed random variables or random process. Okay, there are many ways of being this guy is actually abbreviated, but the most common is I dot D dot. This one, this is. Okay, let's start with just 2 random variables x and y with the probability density fx and fy. Okay, and then if random variables x and y are called independent and identically distributed, if the following 2 conditions are met. One is that the density, distribution is basically the same. Okay, exactly the same distributions. Okay, and second question, second property is that 2 random variables x, y are basically independent. So what that means, and actually this joint probability is given by the product of 2 the densities, right? So if these two conditions are met, it's called IID, and it's a very convenient assumption widely used in statistics. It reflects the situations where the samples are taken from the same source. So at the different occasions you take the different ones, but basically these conditions are met. This can be easily extended to more than 2 variables, and then actually extended that to infinity. Random process can be extended to that random process as shown here. This one is actually 4 variables, but if this one changing to continually along this line, it's a random process, and it can be IID. IID and the wide sense stationarity and actually 2 very often use the terminology, but properties are different. Okay, properties are different. Oops. Yeah, a wider sense of stationarity is that the mean value remains the same. Okay, whereas actually IID distribution as a whole, must be the same. That's much stronger conditions. Okay, and then this one is independent, but oops, oh no, the other way. What am I doing? I lost. Yeah. This guy is actually the autocorrelations is not depending on the particular time. So that's a stationarity. So it's still a totally different concept. Okay. Now, yeah. So after this point is a rather quick review of the stuff that we use quite often from now on. And again, this random this autocorrelation and then wider sense stationarity. These are very important concept. So yeah, I just want to entertain some questions if you have. So let me see. Yeah, correlations. So I think many of you have heard of this, and so for those people that's okay. But to my knowledge, the mechanical engineering students never heard of that. So yeah, I did some quick review. So any clarifications or questions if you have? Okay, yeah. So again, I know one important point is this. Autocorrelation. So this is very important. Okay, autocorrelations are very important. Autocorrelations and the wider sense of stationarity goes side by side, and then autocorrelation 2 time slices to join the the density, probability density, and then we compute the correlation between the two. Okay, and then if 2 time slices are getting close or how far they are, it's basically reflecting some kind of frequency characteristics too, right? So if you take the Fourier transform, you get the so-called power spectrum, and that's actually very powerful tools in signal analysis. Okay, now what I'd like to do today is to go to the applications of this. It's not interesting. It's just learning the definitions and the stuff. So let's look at the more practical and hopefully exciting applications of where these probability theory are being used.
Professor, I believe there's a question in chat.
Oh, okay. Let me see. Chat, stop sharing. Chat. Hi, Blake, right? Okay. First, difference between autocorrelations and autocovariance, right? So, first, it is clear, if you look at the definitions and covariance, we take the we take this and actually a mean value subtracted from this, right? Subtracted here. When you take the auto correlation, we don't take that the mean values, okay? And they're taking this, but oftentimes we see the process as mean centered. In other words, we subtract the mean values, and so auto correlation to auto covariance are sometimes used in an interchangeable way. So that actually makes the terminology a little bit confusing. But correct the definition is that the autocorrelation, we don't subtract the mean value. Autocorrelations, we look at the only variations from the mean value. So now the question is that what happens if mean values go up and down, right? But surely that is not actually wide sense stationary process. It is actually violating this rule. So if mean value varies, actually that's not the case, right? So even though if you look at the autocovariance, but this particular values are changing, that's not actually wide sense stationary process. So that's for sure. Now, another question I think Blake is asking is that, well, this one is actually for all the t, right? But that's actually mathematical, exaggerations. In practical sense, this kind of property must be held for some reasonable time span. In between, you have many sample points in between. Yeah, that's true, actually. So if the process goes up and down gradually, if you take some enough sample points or time windows, yeah, this the type of assumption, wide sense of stationarity applies. The reason why we assume the wide sense of stationary process, oftentimes we like to define autocorrelation, and we like to use the power spectrum. That is actually it cannot be defined if the process is not stationary. So that is actually the reasons why we assume this in many cases. But practical situations, we often deal with these situations where things are varying very slowly. Yeah. So that's actually what I can say to you at this point. As we deal with the more specific cases, we discuss what those assumptions really mean. Okay, now let's look at this adaptive noise cancellations and one application. So yeah, here's the situations. Before this, and I should talk about the active noise cancellation, and that is a technique to measure the background acoustic noise and subtract it from the main signals so that the main signals may be noise free. So here's the concert recitals being recorded. So one microphone is actually put into this piano, and another microphone is taking noise from the background. Some people hear the coughing, or someone is whispering here. Yeah, that kind of noise should not be recorded here, right? But to some extent, such noise is actually captured here. How you can actually reduce that? Or in this case, a pilot is talking to his co-pilot, but it's very noisy environment, and the engine noise is very huge. He has to shout. Instead he just uses this special microphone, and having not only the main microphone taking his voice, but also the other microphone is actually heading towards the environment, taking the background, jet engine noise, and then actually subtract that one over here, right? Or more importantly, when you share your office space with someone else, you don't want to be bothered by the conversation by other people, right? So how many of you really use the special headphone having the active noise cancellation properties in it? It's not the written there. It's now the very standard techniques these days. But many of you are using that, right? because you don't want to be bothered by someone's noise. So let's see how it really works. Basically, active noise cancellation, and then actually more advanced one is adaptive noise cancellation. How it works is this. So here's the true signals coming from the piano, and this is noise background signals, right? So if you actually capture this, one technique is that so this microphone one, which is main line, is somewhat contaminated with this actually noise coming through this, right? So what we like to do is to subtract the effect of this guy. So one naive way of doing this is just to use the second microphone and capture this noise and subtract that one, from this microphone one signals. Okay, hopefully, this one, captured most of the noise over here, and with the particular parameter tuning, you can actually, negate the effect of this interference. However, the challenge here is that, say that the noise coming through these channels may propagate through the air and actually, arrive at the microphone one, right? And there's some dynamics between the two, which we don't know. Some kind of a dynamics is involved, and then arrive at this point. So if you subtract this signal directly, from this microphone one output, you may not be able to really subtract, negate, null out this, WT, which is the net effect of this guy when it is captured by microphone one, right? So one step further from this point is to go to adaptive filtering. What that means, basically adaptive filter is to reproduce this guy. So it is in a sense actually online system identification, right? So if we know this process, then we measure the signals, we should be able to reconstruct this WT over here through this adaptive filter. If this guy is almost exactly the same as this, interference dynamics process, then we should be able to reproduce this guy over here, which may be more effective to cancel out this guy. Of course, the challenge is that we don't know what this actually, dynamical process, right? Yeah, this is to, have some kind of, dynamic properties. So, sorry if you hear the my dog is, barking. She's somewhat not happy. But anyway, so what we'd like to do is to identify this guy or estimate the parameters associated with this dynamics over here. That is actually technologies are being used. Okay, so background noise VT propagated through an unknown dynamic process and then actually arrive at the microphone one, where the true signal is mixed with the interfering noise WT over here, and then resulting in YT. The background noise picked up by microphone 2 is fed to adaptive filter, where the interfering noise is recovered, right? So predicted interfering noise W hat, so we put the hat because this is the estimate of this one, not the true one. It's sitting on your computer. It's not. This is the real physical one. This is actually estimated one. Okay, subtract this one from YT. Hopefully, we can recover the original signals. Okay, so yeah, first let's actually formulate this particular part in the interference dynamics. By the way, this is actually introduction to your context-oriented project one. So that is to cover the many topics involved in the previous lectures. So I know first topic to apply, first the theory to apply is this one, finite impulse model. Remember what that means? This is basically impulse response model. Yeah, sorry, finite impulse response. Response is missing over here. That's a typo. Finite impulse response model, FIR model. And that is to represent the input-output relationship by the simple linear expression, right? So input is at this time is Vt. And we take a one time step back, Vt minus 1, and then 2 times step back, T minus 2, and down to T minus M. So we set the this M time slice time windows. And then we basically represent the output as a linear combination of these, where B1, B2, Bm basically comes from impulse response. We use the G's, in the previous lectures, but that's actually, comes into this place. So what we like to do is to estimate the parameters B1, B2, Bm. Put it into a parameter vector theta. This has been used many times, right? And then the rest of part is regressor. So Vt minus 1, the Vt minus m are actually regressor inputs, okay? And if we use these two vectors, this, Wt, this guy can be written as a linear regression. Okay, now what we like to do is actually, usually regressor comes from the input, and the input in many, situations, that's the input we create, we provide, so we know it, but in here it's not known. So we use a little bit different techniques, but, we, still call this a regressor. That's actually, independent variables, and this one is, dependent variables. Okay, it's a linear regression. Now, big assumption is that the true signal xt comes into this guy, and the background the noise, this guy, are uncorrelated random processes, uncorrelated. Okay, this one is a major, assumption. So if you take the an expectation of the product between xt and the xt minus tau, okay, expectation is 0. And also this is a very strong condition. This is valid for all t and all the tau. So this is a similar, this is basically the same thing, random variables x at the xt1, and then another random variable, Vt2, are uncorrelated, okay? Uncorrelated. The process doesn't have to be a wide sense stationary, but what we expect, assume is that, two random variables, each time slice, random variables, two random variables are uncorrelated for all the time slices, t and the tau. That is actually a big assumption we make. Okay, now how we really do that? So here's the things. We first, proven is to estimate the parameter vector theta in real time. Okay, real time. So, in adaptive filter is basically we like to reconstruct this guy, right? So theta is involved in this, adaptive filter. And with that, we can actually cancel out the effect of this guy, right? So the noise may be most suppressed. The approach is the following. We consider the recovered output ZT. So after subtraction, subtracting W hat, we get the ZT. This is one, to be recorded, or this is to be presented to you, right? So this one is basically YT minus W hat, okay, W hat. Okay, first let's actually compute the mean squared signals of ZT min and T. I put the slash theta hat because this ZT includes W hat, and the W hat depends on the parameter values being used in this filter, right? So in a sense, this ZT is basically depending on the theta hat. So we put it this way. Okay, now what we like to do is they take the square of this ZT theta hat. In other words, actually, this is in a sense actually power strength of this signal ZT, and we take the expectation of that. Now, by definition, ZT can be written this way: YT minus W hat. And further, YT is basically comes from the true signal XT and the WT. So let's use that relationship over here. YT replaced by XT plus WT minus W hat, right? Now what I'd like to do is to expand this, but I know we put the D's to be 1. Okay, and then expand it. The first one, XT square, and the 2 times XT times this guy, expectation, and then this square at the last term over here. Okay. Now, interestingly, we get some important property from here. That's actually in here it is actually include XT times the WT. Let's examine this guy. Expectation XT WT. And the WT is basically written in this way. We can actually go back and remember that the WT is a linear regression, right? Linear regression. It is basically the product between parameter components and the regressor components. So this is the finite impulse response model, right? So let's put this one into this. So that is actually WT is expanded into this, right? And the B1 to BM are basically constants. So we can actually factor out the B1 and then, apply this expectation operation, which is the integration operation, to each term. So we can divide this one into these M terms, right? So what do you comes into your mind? You see that the expectation XT times VT minus 1. So this is actually expectations of a product of 2 random variables, right? That's basically what? Correlation. And we did assume that the true signal XT and actually background noise of VT are uncorrelated, correlation or orthogonal to each other. And then that applies to every T and then every tau. So all of these terms are basically 0. So we can conclude this cross term is 0. Okay, likewise, in this particular part, W hat is actually using the B1 hat to BM hat, doing the same thing. We can conclude this one too is 0. Okay, now next one. So what we'd like to do is basically we started with the computation of this last after subtracting this guy we get the this result of ZT, and then we computed the squared basically power of that output to ZT, right, expectation. And then by expanding this we had the XT terms. And these 2 terms basically we evaluate the correlation. They are not correlated, so we eliminated these two. So remaining part is this and this. Okay. Now this particular part is very much important for us, right? Because our objective is to actually tune this adaptive filter with the simple the linear regression structure having a parameter the theta 1 to theta n, and this output should be the same as this, right? So if you treat these WT and the WT and the W hat T are actually outputs from the real process. In fact, it's a real process, and output from a model. What we'd like to do is to actually make the difference between the two smaller, by actually selecting the right parameter values, right? So our objective is to minimize this. Okay, so that is what we need to do. However, we cannot actually access WT, right? This includes WT. We cannot access this. But if you add this term, and our objective is to minimize this guy, with respect to theta. But this xt, this does not depend on theta. So, what we can do is, not directly try to minimize this, prediction error squared, but try to minimize this output z square, which is actually accessible. We can detect that, right? And minimizing this with respect to theta is the same as minimizing this guy with respect to theta, because this xt is not the function of theta, right? So, here's the things. We like to optimize, we like to minimize this squared prediction errors with respect to theta. That's the same thing as doing this, because this is not a function of this. So it's the same thing as this, right? So here's the thing. So maybe we can actually go back to this. So you remember that the prediction error model formalisms. What's that? Maybe I can write it. Let me just change this to my iPad. Yeah, so you remember that there's a real system, and here's the model, and the prediction error formalisms is to compare these two, right? So this guy is y, and this is y hat, which is actually functions of the theta, right? ABYT. And we like to minimize this square of them. Prediction error need to be minimized, right? So now our situation is, instead of YT, we have the WT, and here W hat T theta, right? In our program. Maybe we can erase this. Yeah. Right. Yeah, this is our situation. Okay. Now, and also I would say that W2 is not directly accessible, but in fact, what you see is here. This is the BT, and here's the XT, that the true signal is added, and what you get to here is not the WT, but I know we get the yt, right? Yt equals xt plus w, right? Remember that this is the true signals, and then the noise comes in. On the other hand, this side, we have the w hat is actually accessible. So if we actually add the xt over here, we can make an apple-to-apple comparison, right? So y hat is basically x plus w hat, right? W hat, and the difference is basically w minus w hat, which is something we like to minimize. But remember that the this xt here and here does not contribute to minimizations of that output power, right? So even though we eliminated this, we can do the same. So that is something we are doing in this formulation. Even though we have x and it comes in, but let's put this one aside because this one does not contribute to any of the minimization problem here. So if that's the case, this is a true system, this is a model system, both actually producing this predictions and real output, and then in some way this is to take the difference between the two. So with this we can say that let's see, treating wt minus w hat as a prediction error, okay? And then now we because of this mass, we can replace this error by zt theta, and if this is computable, we can apply the recursive least square algorithms to estimate the parameters involved in the interfering dynamics FIR model in real time. Perhaps you need to use a forgetting factor, so that it can be updated all the time. So this is the algorithm that we can use. Remember that with the forgetting factor, alpha is sitting here instead of 1, right? And then this is actually multiplied to this. So yeah, yeah. So here's the things. How we actually adapt this, make this filter to be adaptable to the unknown situations. We form a recursive least squares over here using a ZT, as a just prediction error. In terms of the minimization with respect to the theta, it is basically no difference between minimization, the error, prediction error minimization with respect to W versus ZT, basically the same thing. So we form this recursive least square loop into this. Okay, so this is to be involved in the project, the number 1 context-oriented project. So let's discuss that one. Where's that? Let me see. Oh yeah, maybe this guy. So this is the statement of a context-oriented project number 1, which I posted already. Have you seen that? Have you had the chance to look at that? It's a module, one's canvas. So yeah, the title is Motion Artifact Resistible Wearable Sensors, right? And it's today, released today, and then due is September 28th. And we have a chance to discuss this at the study group on Friday, September 25. Okay, So, here's some context, to motivate you. Wearable medical sensors monitor the patient vital signs anytime, anywhere, continuously. That's wearable sensors. These sensors are expected to revolutionize, blah, blah, blah. Yeah. Well, I was almost rewriting, this, project one statement in the context of COVID-19, but it's not actually, medically proven, so I wouldn't say that, but there's a very interesting connection to that. Anyway, so yeah, these sensors are expected to revolutionize the health services, including a diagnosis, treatment in the home for diabetes, hypertension, pulmonary disorders. So that's going to COVID, and it's already applied to fitness and exercise stuff. The challenge is that the motion, right? It must be really robust, and how you can actually deal with the, accelerations and, movement of the wearer, right? So we use adaptive noise cancellation techniques in doing this. So yeah, figure one, yeah, sorry about this, my group worked on that almost 20 plus years ago, and this is a very crude first prototype. It's called the MIT ring, and it has a photoprecisionograph in it, and it has basically LED at the particular wavelengths, and then the photo detectors in it, and also comes with the MEMS accelerometer. At that time, people, IMU is not existing, but at a more primitive version, MEMS, mechanical electrical microsystems, if I'm correct. Okay, so that's basically motion acceleration is measured at this point. Okay, so two sensors are actually in the same package. Okay, so this block diagram is slightly different from the one that I talked about today. I just took this one directly from my older paper, but the basic concept, right? So we use not the two microphones, but one is a photoprecisionograph sensors. The other side is to detect the emotion, so it's accelerometer here, but the same thing. This is microphone one and microphone two. Okay, and what you like to do is to develop this adaptive filter to basically mimic this actually distortion process. Okay, how acceleration is to distort the waveforms, otherwise very clean pulse signals, right? So we assume that this FIR model, sorry, a little bit of different notation because this is accelerations, right? And then what we like to do is to minimize this prediction errors, right? And it turns out it's basically the same thing as the minimizing this, output power, right? And the first step is to get to familiarize with the, recursive least squares with the forgetting factors. So first, assignment jobs is to implement this, above algorithms using MATLAB. So of course, if you look at the MATLAB, system ID or some toolbox, you can find the nice code of MATLAB recursive least squares. Okay, but what I want you to do is to code it on your own. Yeah. So but MATLAB is very easy to code to some extent. So code it on your own. And actually translating this one into some code is a very, simple process. However, you need to debug it, right? So oftentimes the students learn a lot, through debugging process. It must work. And then actually we provided some test data. It should show the expected result, right? So you can test out your program by running this. And then actually after you feel comfortable with the this recursive least square algorithms. Then we apply it to this, real, active noise cancellation program, right? You can download some of the data from Canvas. Nick Selby created the new folder. It's a context-oriented project. In that folder, you see a few data files, and please download those data files. Use for this and actually a project. And now I have a mixture of some extra credit programs and something mandatory questions. And the question C is actually after you run this, a lot of deeper questions. The data set in part B of the above question is a special case where lies in a hyperplane of dimension lower than that of parameter vector theta. So what I mean by this is not actually persistently exciting, right? So it's not as persistently exciting, and story is just a cone field driving. You remember that? Just same input coming in repeatedly. What's going to happen? This the recursive least squares with the forgetting factor that tends to blows out, and I want you to look into that issue. And then you can address why that happens, a bit more mathematically. It doesn't have to be very theoretically thorough, but you need to be able to explain that. That's the extra credit problem. Okay. Now going down here, we apply this adaptive filter and then test it. Yeah, and I hope you can find the good result coming out. Yeah, these are references that you see more of the background story, and then it did actually recover the the badly distorted PPG signals is basically recovered, and a very good reliable signals are obtained, even though you move a lot. Now, this extra credit problem, create your own data for PPG and acceleration, the signals, and also create your own true model and its output in response to acceleration. From this point, it's actually open, very much open questions, and then you create some data, okay? In generating the data, attempt to correlate the acceleration with the true PPG signals to a certain degree. So what this means is that back to this diagram. Remember that the big assumption is that this signal is not actually involved in the signals captured here, right? These two should not be correlated, okay? Absolutely not correlated. But for some reasons, body motions and your pulse are correlated. For example, sometimes the jogger, they synchronize their stride with their heartbeat, right? If that's the case, there's some correlation between the two that happens. Well, you can create such data. This one is partially, this signal is partially involved in here, right? So if that kind of situation happened, what is the effect of that? And that's actually being asked here. This is actually a little bit more advanced question, so it's extra credit. But if this kind of project is very much open-ended, so we welcome any kind of issues. Okay. The last question is also involved in the these are all topics that you can discuss at your study group meetings, right? Study group meetings. You can discuss these and then exchange ideas. Does that make sense? So maybe a reporter, you rotate the reporter roles within that study group, right? The reporter at this time is needing a little bit more job preparation, and the other members too, they need to work on it a little bit more. But it will be very interesting. You get the much more solid understanding about the materials. And then actually, whether the signals are correlated or not, this is a fundamentally important aspect. And then when we move to Kalman filter, we use this. But I know Kalman filter, if you just study theory, these two are uncorrelated, just cancel out, slash out, blah, 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 and this is the final result. Don't ask why, just use this. That's not the proper way of studying this. But before doing that, I really want you to experience how the signals, correlated. And in case they are not correlated, we can actually slash out, right? So that is something difficult to observe. Yeah, conceptually, mathematically, you understand it, but it's really hard to observe. So the best way is really looking at the signals and compute something, and then actually experience how it works. I really want you to do it before we go into Kalman filter. And then that is a very valuable experience, very pedagogically valuable experience. So coding things this way, that takes a little bit more time, but don't blame me. This is actually worth doing. So I hope you can do that. With that, any questions or comments or any clarification? Oops, yeah. How do you ensure that the microphone 2 doesn't capture the truth? Oh, yeah, okay. Anubhav, you ask a very good question, very good questions. So, so this is just, as I asked the last questions, in the project, the last question. Yeah, if that one is, and true signal sneaks in to second microphone, you see something interesting behaviors. Yeah. I want to disclose the answer, but you can address that in your project. Is there a reason that there is no? Oh, okay. So, Alex, you ask, one important question, why it does not, say in the WT, yeah, B times V, T, we did not include that, right? Yeah, so, well, if the system is continuous systems, because of the causality reasons, we do not include that, VT. Rather, we start with the next time instance, right? Yeah, but discrete time system like this, yes, we can include that, not VT, but that highly depends on the applications, and also how you do sampling. So yeah, I in my lecture notes, I use starting with the VT minus 1. To avoid some of these subtle issues, but in many cases, not all of them, in many cases, you can include that, yeah, for the discrete time systems. And continuous time system, no, but discrete time systems, yes. FIR can include K equals 0 term, not sure why. Oh, yeah, that's the same question, Brian, right? Maybe it needs one time cycle to compute the adapted. Yeah, so initial conditions, okay. Yeah, so when the system, gets started, right? The system has no clue as to what is actually the true values of these FIR model parameters, right? So for a certain time, it does not actually produce the right one. So actually, it has some kind of delay. But after collecting the certain data, it is basically guaranteed to converge to, forget about the forgetting factor. It is guaranteed to converge to certain parameters. parameter values. Even though you started with the randomly picked initial values, it is to converge. As far as you provide the initial P, matrix, P not to be, positive definite, usually we use identity matrix with that, and that is going okay. But adaptive filter, it adapted to or reacted to the real systems, so it takes some time. Of course, quick convergence is necessary, but it takes some time. Yeah. Okay. Any other questions? Anyone? Would it be fun? So it is actually going to a little bit involved, but I know these are stuff I hope you can do. Yeah. Okay, with that, yeah, I'll see you next week. And I know Nick will actually entertain your group meetings on Friday. So, starting with the PS number 1. That is very simple. Yeah. Okay, good. Nice to see you. Take care.
Thank you.
Yeah, bye.